This is Daryl with Cisco Hands-On Training, episode 26. Today we're going to get into Bgp Route Filtering. Now if you remember, Bgp is the Border Gateway Protocol, which is for use between autonomous systems. And one of its main abilities is to filter routes and to implement route policy in a much more flexible way than our other routing protocols. In RIP, for example, or in RIP you can filter based on IP addresses, but in BGP you can actually do filtering based on the autonomous system number. So you could say, for example, I don't want to accept any routes that go through autonomous system 65,314. For today, we're just going over BGP route filtering. In a later episode, we'll make routing decisions based on these criteria. So today, we're just accepting or denying routes. And there are several different methods of route filtering. The first I want to talk about is a distribute list, which is simply, we're going to have an access list, it's going to match an IP address range, and then for a neighbor, we're going to apply the distribute list, and that distribute list will either permit or deny that particular route from being accepted. The problem with the distribute list is this distribute list, it looks like it will match the route 10net/8, but it will actually match anything inside the 10net as well. So it would match a 10net, it would match 10.0.0.0/8. It would match 10.0.0.0/16. It would match 10.0.0.0/24. It would match 10.3.3.2/31. It would match anything in there, so you don't have that much control. If you want to match a specific route advertisement, you can use a prefix list. So here's a prefix list, and it permits the 10net exactly, 10.0.0.0/8, and that way if you have a more specific one, you can choose exactly which net masks to accept. Another way you can filter your routes is by an autonomous system path list. So you can, for example, in this syntax, the caret means it matches at the beginning of the autonomous system path attribute, which again is a mandatory attribute, and it matches an autonomous system path which starts with autonomous system 65,001, and then it has white space going to 65,002, and that's the end. So this autonomous system path list will match an autonomous system, will apply to all routes which have exactly two autonomous systems in the path. The first is 65,001 and the second is 65,002. So in other words, your autonomous system attaches to autonomous system 65,001, which attaches to autonomous system 65,002, which is where the route originated. That's the $sign. Then it would match, and in this case we're going to permit routes that match that. Another way to filter lists is also controlled with an access list, but is using a route map. A route map is a more flexible way of implementing routing policy in BGP. In the earlier examples, we were either permitting or denying routes. In this final example, we're still just permitting or denying routes, but we're using it with the more complex route map. Now, why would you want to do that? Well, if all you're doing is permitting or denying routes, you don't. But in a route map, you have the ability to do other stuff. A route map has a stanza, and inside each stanza, you match something, and then you set something. In this case, we're just matching, which means that we're permitting or denying the routes, and then later, and that's it. In the next episode, we're going to implement route policy where we're going to match and then we're going to set. So those are the different methods of route filtering. Let's get into some examples. Here's our map for today. It's the same map for last time. We have two autonomous systems. Autonomous system 65,001 with one router at the top. Autonomous system 65,002 with two routers at the bottom. The bottom autonomous system is originating two routes. One of the routes is 172.17.0.0/16. That route actually is originating from the middle router, and one route is 172.18.0.0/16. That route is originating from the bottom router. I'm going to do all my route filtering on the top router today. So what I'm going to do is, for these two routes, I'm either going to accept them or deny them from my two neighbors, and that way we'll be able to see the impact. So I'm on the routers. So show IP BGP sum. You can see I have two BGP neighbors up. I am autonomous system 65,001. You can see that up here at the top. My local autonomous system number is 65001. My BGP table version is 4. And down here at the bottom, I have two BGP neighbors. They are eBGP neighbors because my autonomous system is 65,001 and they are each 65,002. They've been up for about 10 minutes. And I have the number of messages received and messages sent and the table version. And my in queue and out queues are both 0, so it's empty, so I don't have any messages queued up. And let's look at the BGP table. Show IP BGP. So here on this router, I have 172.16.0.0/16. That is a route that I am originating on the top router, and I can tell that because the next hop is 0000. And the path is just I, which means there's no autonomous systems in the path, and it's originated by IGP, which means it's originated with the network statement and a corresponding route entry on my local router. In this case, I'm using a static hold down route. And then I have two other routes. I have the 172.17 and 172.18. 172.17, I have two next hops, and both of them have the same autonomous system path, which is 65,002. Both of them have the same origin code, which is IGP. And then for 172.18, same deal. Two next hops, both of them have the same path. However, look at this arrow here. This arrow means best. These two routes, on both of them, I've chosen the 172.16.2.2 as the next hop. Back on our map, 170.16.2.2 is the middle router. If you remember, one of the routes is originating from the middle router, and one of the routes is originating from the bottom router. But on the top router, I think that I should go to the middle router on both of those routes. Why? Doesn't it make sense I should go to the bottom router for the 170.18? Well, the answer is, how do I know that? I make a routing decision based on the BGP routing criteria. And my autonomous system path is the same. It's one AS hop. My local preference is the same. My metric or multi-exit discriminator is not set, so it's the same. I have not configured a wait, so that's the same. What decision criteria do I use at the end? At the end, I use the lowest IP address of the neighbor. And 172.16.2.2 is lower than 172.18.2.2. So I will choose the lower IP address, and the 172.16.2.2 becomes the best next hop for both routes. Now, what if I wanted to change that? Well, that's what we're going to talk about in the next episode, which is where we make decision criteria. For right now, let's just start filtering some routes. So the first way I wanted to filter is based on a distribute list. So let's say that I want to deny 172.16. I want to deny the first route, 172.17.0.0/16, from coming from this router, the 172.16.2.2 next hop. Okay, so I need a distribute list. So I need an access list. So access-list1, and I want to deny a particular route. So access list 1 deny 172.17.0.0. And what do I use for my don't care bits here? Usually I could use this 0.0.0.0, and that would match this route. So I'm going to go ahead and do that. Access list 1 deny 172.17.0.0.000. And then access lists have an implicit deny at the end. So if I do nothing else now, it will deny everything. So let me do an access-list1 permit any. This is a standard access list because it is between 1 and 99. So it has an IP address and a set of don't care bits associated with it. And that is my access list, router BGP 65001. I apply the distribute list to, so the access list, I'm going to use it as a distribute list. I'm going to apply it to the neighbor statement. So router BGP 65001, neighbor 172.16.2.2, distribute-list1 in, and I'll do a show IP BGP. So I've applied I created an access list, I applied the distribute list to the neighbor, and I'm doing show IP BGP and nothing has changed. Well, let's double check I did it right. Show access-list1, and it looks like I'm denying 172.17.0.0 and I'm permitting everything else. And show run pipe begin router BGP. And I have applied the distribute list 1 in an inbound direction on this neighbor. And if I do a show IP BGP, it still has not taken effect. Why not? Well, the reason it hasn't taken effect is because in BGP, the route filters that are in place are only applied when you receive the route. And I've already received the route. I've already processed the route. I processed it into my route table. In order to process this, in order to have this new routing change take effect, I have to reprocess the incoming routes. What I need to do is I need to clear my neighbors. So clear IP BGP 172.16.2.2. This is going to clear the neighbor 172.16.2.2. Oops, look what happened. My BGP neighbor went down. This is what's called, I'm clearing the BGP neighbor, but this is a hard reset. So it actually takes down the BGP neighbor, and the BGP neighbor will eventually reestablish. It can take up to a minute. And during that time, the BGP neighbor relationship is down, so I'm not sending any traffic over this path. So this is an impacting outage here. That's not great. Okay, now the neighbor's back up. Show IP BGP. And we can see that the neighbor is back up, and now my routing change has taken effect. Okay, so there are a couple lessons here. The first lesson is when you apply a distribute list in BGP, or a route in general, a route filtering change, you need to clear the neighbor in order for the BGP filtering change to take effect. But if you just do that in the way I did it, just clear IP BGP and then the BGP neighbor, it will reset the BGP neighbor, and the BGP neighbor can be down for 30 seconds, 45 seconds. That's impacting. So if you make a filtering change and then you fail to clear the BGP neighbor, then the BGP neighbor, the filtering change is still in effect, it just applies to new routes. And then if a month later your router reloads, or a week later you receive a new set of routes, then those route filters might take effect when you're not expecting it. So you really want to clear your BGP neighbor when you make a filtering change to make sure that the change that you configured was correct. You'd hate to configure something, have it not take full effect, and then a week later there's a router reloads or a BGP neighbor just resets for some other reason, and then your routing's all messed up and you have no idea why. You want if you do something wrong in your change window, you want to learn about it and fix it in your change window, not when you're off doing something else or sleeping or on vacation or you don't want to get paged in the middle of the night to fix something. Okay. What did we just do? We created an access list. We used it as a distributed list. We applied it to a neighbor. We did a hard BGP reset. Let's do a prefix list on the other neighbor and, let me remove that distributed list. So conft router BGP 65001, no neighbor 172.16.2.2 distribute -list 1 in. Show IP BGP. Show IP BGP. Let's see, I just eliminated the distribute list, but it still seems to be in effect. Let me do a show run pipe begin router BGP. And here I am doing show run pipe begin router BGP, and you can see there's no filtering at all. But if I do a show IP BGP, the route filter still seems to be in effect. Again, I have to clear the neighbor. Let me try to clear the neighbor in a less impacting way. Conft, actually I don't need to be in conft. Clear IP BGP 172.16.2.2 soft in. This is what's called soft BGP, a soft BGP neighbor reset. And then if I do a show IP BGP, here you can see that now the filtering is gone, and that was not impacted. So instead of doing clear IP BGP and then the neighbor, you do clear IP BGP soft in, and it does a soft BGP reconfiguration in the inbound direction because I'm affecting my inbound filtering, and that's cool. That's not impacted. So you want to get in the habit of clearing your BGP neighbors, but you want to do it in a soft. You want to do soft BGP neighbor configuration. Okay, let's deploy a prefix list. Conft IP prefix -list Bob permit 172.17.0.0/16. What is this going to do? It's going to permit the route 172.17.0.0/16. So it will permit this route, but it will implicitly deny every other route. Because just like an access list, a IP prefix list has an implicit deny at the end. So let's apply it. So conft router BGP 65001 neighbor 172.16.2.2 prefix -list Bob in show IP BGP, and again the filter change is not taking effect, so clear IP BGP 172.16.2.2 soft in show IP BGP, and there it is. On neighbor 172.16.2.2, The only route that is being allowed in is 172.17.0.0/16. All other routes have been denied. Well, there was only one other route that we were previously receiving. It was 172.18.0.0. Because that's now denied on this next hop from this neighbor, that means for 172.18.0.0 there is only one next hop left, which is the other neighbor. Okay, that's a prefix list. Conf T, router BGP 65001, no neighbor 172.16.2.2 prefix dash list bob in. So let's do an AS path access list, and every route that we are receiving has an AS path which is exactly 65002. So let me create two AS path access lists. So conf T IP AS path access dash list to permit caret 65002 $. This matches an AS path that begins, the caret means begins, and then 65002 is one autonomous system number in the path, and then $ means the end. So this will match an AS path with one autonomous system in the path, and that one autonomous system must be 65002. And then IP AS path access dash list 3 permit. Let me give a different AS path which will result in a denial. So caret 65001 underscore 65002 $ symbol. This will match an autonomous system path that starts with 65001 and then has a white space and then ends with autonomous system 65002, and I've got the $ at the end, forcing it to be at the end. And let me apply one of those to each of my neighbors. Router BGP 65001, neighbor 172.16.2.2, remote 172.16.2.2. This is a filter list, filter dash list 2 in, and neighbor 172.18.2.2 filter dash list 3 in. So filter list 2 should match the routes we're receiving there, and filter list 3 should deny the routes we're receiving there. So let me clear my BGP neighbors. I'm going to try to do it soft. Clear IP BGP star for all neighbors, soft in. Now let me do a show IP BGP. What I expect to see now is I expect to still see both routes via this neighbor, 170.16.2.2, and I expect not to see any routes via my neighbor 172.18.2.2. Let's see what we saw. And we are not seeing what we expect. Neighbor 172.16.2.2, we still receive both routes on it. Neighbor 172.18.2.2, we still see both routes, and we were expecting not to see it. What happened? We did the BGP neighbor soft reconfiguration inbound. Well, let's look at our neighbor in more detail. Let's look at our neighbor show IP BGP 172.16. Show IP BGP neighbor 172.16.2.2. And in the neighbor here, the BGP neighbor is 172.16.2.2. The remote autonomous system is 65002. The BGP version is we have the remote router ID, which is the loopback on the remote router, 172.17.1.1. The BGP state is established, and neighbor capabilities, route refresh. advertised and received old and new. This neighbor capability is something that I believe is necessary for the soft reconfiguration to work. So let's go ahead and look at the other. In fact, route refresh requests. We've sent 3 route refresh requests. Let me clear my BGP neighbors again, and then look at my BGP neighbor again. And now the route refresh request we've sent 4. So every time I do a soft BGP neighbor reconfiguration, it sends a route refresh request, and this neighbor has the capability of handling route refresh requests. Let's look at our other neighbor, 172.18.2.2. This neighbor just has route refresh advertised. So it does not have the route refresh capability for received routes. And so the soft BGP neighbor reconfiguration is not working here. Now the reason is because the bottom router is running iOS 11.3 and the middle router is running iOS 12 something. So the bottom router is running an older version of iOS, and it just doesn't understand it just doesn't have the route refresh capability. Let me try something just for kicks. conft router BGP 65001 neighbor 172.18.2.2 soft. Soft dash reconfiguration inbound. So I did the neighbor 172.18.2.2 soft reconfiguration inbound. As soon as I did it, the neighbor went down with a soft reconfiguration change. Show IP BGP. Show IP BGP sum. The neighbor went down with a soft reconfiguration change. The neighbor is active. I expect that neighbor to come back up in a few seconds here. And now my neighbor is back up. So that neighbor has an older version of iOS, but to adapt to that, I was able to use the soft reconfiguration inbound neighbor statement. And let me look at my routes. At this point, my routes are what I'd expect based on my new filtering. Again, let's review the filtering. Show, run, type, begin, router, BGP. So on neighbor 172.18.2.2, I have a filter list 3 in. And the filter list is an AS path access list, and it permits only an AS path which I'm not going to see. So every route, every BGP advertisement that I receive is not going to match this, and so it will go on to the implicit deny. So I expect all routes that I receive from this neighbor to be denied, and that's what I'm seeing. Show IP BGP. I'm not accepting any routes from that neighbor. Let me see if I can pull up what routes I'm receiving. Show IP BGP neighbor 172.18.2.2 question mark received. Dash routes. And you can see that if I do the show IP BGP neighbor 172.18.2.2 received dash routes, I am receiving 2 routes from that neighbor. And so this is nice because it shows me what routes I'm receiving before I do the filtering. Let me do a show IP BGP neighbor 172.18.2.2. and my neighbor capabilities have not changed. It's still just route refresh advertised, but inbound soft reconfiguration is now allowed. And the reason it's allowed is because I configured it. Basically what's happening is I am saving the route information that I received, and that way if I adjust my filtering, it can take effect immediately without an impacting outage. So that's what the soft reconfiguration inbound command does. Show run type begin router BGP. And you can see that I saved the route advertisements because I was able to do the show IP BGP neighbor received route. So here's the soft reconfiguration inbound command, and now let me remove the filtering. Conf T, well, if I do a show IP BGP, again you can see our route is filtered. So conf T router BGP 65001 no neighbor 172.18.2.2. Now, I'm in the middle of typing a command here, and I'm going to type no neighbor 172.18.2.2 filter -list 3 in. But if I accidentally type return right now, I will blow away the complete neighbor config for that neighbor. So when you're typing commands in BGP to remove a line in your neighbor config, don't hit return too soon. Always think before hitting return, especially when dealing with BGP. So no neighbor 172.18.2.2 filter -list 3 in. Show IP BGP. My filtering change has not taken effect because I have not done a BGP neighbor reset. Let me try a soft reset. Clear IP BGP 172.18.2.2 soft in. Show IP BGP. And now you can see that when I clear the BGP neighbor soft inbound, this time it worked, because now I have soft BGP neighbor reconfiguration enabled on this route. So when dealing with old versions of iOS on remote routers, the soft reconfiguration inbound command is useful because it enables soft reconfiguration, which means you can make BGP filtering changes in a non-impacting way. But when you first configure it, it has to do a hard reset on the BGP neighbor. So, and that's because because the soft reconfiguration inbound command saves the BGP advertisements that you've received. But it can't go back in time and save the advertisements you received yesterday. It has to clear the BGP neighbor in a hard way, re-receive all the advertisements, and while it's doing that, it's saving it. Now, what's the downside of soft reconfiguration? It uses more memory. So if you have 200,000 routes in your BGP route table, well, then it's going to use a lot more memory. But frankly, it's memory worth spent. If you don't have enough memory to do soft BGP neighbor reconfiguration, it's worth spending the money to buy some more memory. Okay, so that's an AS path filter, and it's now removed. Now let's do a route map where we have show access -list 1, and we already applied access list 1 directly to a neighbor with a distribute list. Let's apply it with a route map. So conf T route -map Joe permit 10. This 10 is the number in the route map. So route map Joe permit 10, and then match IP address 1, and that's it. We'll just have one entry in our stanza right now. So let's do a show route map. If I do a show route map, the sequence number in the route map is 10. There's only one stanza. The sequence number lets me create new route map entries ahead or behind. So I could type route map Joe permit 5, and that would be interpreted before this in sequence. My match clause, route maps, each clause in a match, each route map stanza has a match clause and a set clause. The match clause identifies what routes it applies to. In this case, it applies to routes that match access list 1, which is all routes except 172.17.0.0. The set clause is empty, which in this case means permit. I'm not setting anything, but because I match something, it's permitted. So let's apply the route map to a interface. Const router BGP 65001 neighbor 172.16.2.2 route-map Joe in. Show IP BGP. Again, no change has taken effect yet because I haven't cleared my neighbor. Clear IP BGP 172.16.2.2 soft inbound. And then show IP BGP. And there you can see I denied the route 172.17.0.0 coming from the neighbor 172.16.0.0. And you can see the only route, that route, I'm now only receiving it from 172.18.0.0. Now for kicks, let's look at a route map with multiple stanzas. So access-list 5, const. Okay, it's doing a domain lookup because it thinks access-list is a host. And now it's doing it again. I'm in the mistake of typing it again. Control-Shift-6X. Control-Shift-6X. Control-CCC. Okay, I'm out. Const no IP domain -lookup. I don't have any DNS servers in my lab, so that's a good thing to do. And then const access-list 5 permit 172.16.0.0. Is that what I wanted? No, I wanted 172.17.0.0. Actually, access-list, call it 4, permit 172.17.0.0. Show access-list 1, show access-list 4, route, show route map. So I've created a new access list, and I'm intending that for a new route map stanza. And I want to permit 172.17.0.0 with that route map stanza. Now the problem is, if I just type route map Joe permit 20, that new stanza will be below route map Joe permit stanza 10. So I need the new route map stanza to be above it. So I'll do const route-map Joe permit 5 match IP address 4. Show route map. So here I have my route map. I have two stanzas. Sequence number 5, which is the first stanza in the route map, matches access list 4 and does nothing other than permitting it. Route map Joe stanza sequence number 10 matches access list 1 and does nothing other than permitting it. Show access-list 4, show access-list 1. So the first route map stanza will match the route 172.17.0.0, and the second route map stanza will match everything except 172.17.0.0. Let me do a show IP BGP, and my new route filter changes have not taken effect. Clear IP BGP 172.16.2.2 soft in. show IPBGP, and as expected, I'm receiving all of my routes. Now, why would we do this? Show route map. Again, route maps are really designed for setting things. So let's, just to give you a preview of the next episode, let's set something with sequence 5. So const route map Joe permit 5 match IP address 4 set, let's set local preference 80. Default local preference is 100. We'll do a show route map. So in this case, routes that match access list 4 will have their local preference attribute set to 80, and other routes which match access list 1, which is everything else, will do not have any set clauses, but they're still permitted. Clear IP BGP neighbor 172.16.2.2 soft in. Clear IP BGP 172.16.2.2 soft in. Show IP BGP. And there it is. You can see that on this neighbor only, for this route only, the local preference is set to 80. There's the 8, there's the local preference, and there's the 8, and there's the 0. I'm sorry, it's scrolling right there. So show route map. So that's a preview of next week's episode, but you can see that's the power of route maps. In addition to matching and just permitting or denying routes, you can actually change the routing policy like the metrics. So I have one correction to make. Earlier, I pointed out that let me turn off my filtering here. So, show run. Router BGP 65001. Let me turn off all my filtering, get back to the default state. No neighbor route map, no neighbor filter list. Clear IPBGP star soft in. Show IPBGP. Okay, one of the things I said earlier was that the reason I was preferring the middle router is because the neighbor IP address was lower. However, looking it up, it is actually the BGP router ID, the lower BGP router ID, that's important. So it's the middle router has a BGP router ID of its loopback, 172.17.1.1, which is lower than the bottom router, which has a BGP router ID of 172.18.1.1. So if I do a show, so I would expect my routes to have the next hop, with all the filtering disabled, I would have the routes have the next hop of 172.16.2.2. Let me do a hard, I think after all my filtering, I'm going to do a hard BGP neighbor reset, clear IP BGP star. And that caused both my neighbors to go down. Now I'm going to pause it for a second and see what it looks like when it comes. Okay, and now I'm back. And you can see after the BGP neighbor reset, the preferred route even though the neighbor 172.18.2.2 came up first, my next hop for both of my routes is with the BGP router 172.16.2.2, and that is not because the next hop IP address is lower. It is because the next hop router's router ID is lower. Let's look at my neighbor, show IP BGP neighbor. Show IP BGP sum. And if I do the show IP BGP in the show IP BGP neighbor, the BGP neighbor is the remote router ID is 172.17.1.1 for the middle router. Okay, so that's what we're going to cover today. Let me do a quick review. We covered 4 different methods of route filtering. We have an access list, which is used as a distribute list. We have a prefix list, which allows us to specify the exact net mask of the routes to permit or deny. So that can be a little bit more specific. We have an AS path access list, which allows us to permit or deny, to match based on autonomous system path, and permit or deny routes based on autonomous systems that traffic goes through, and then we apply it with a filter list. Or we have the much more powerful and flexible route map, where we can match something. In our case, we matched based on an access list, and then we can, in more advanced configurations, we can set something. And that concludes today's episode. In the next episode, we're going to actually make some routing decisions based on our filtering as opposed to simply accepting or denying routes.